Roger, you wanted to go through some preliminary material, I believe.
Yeah, so I've got, when you share screen, I didn't remember it working this way. I don't get to see any of the audience or anything, or the chat. I did. Oh well, but you can see my browser at least.
Yeah. Yes, we can.
Okay. Okay, so the what we're going to go through today, as I mentioned before, it'll probably be a 2-week session. We're going to be ultimately reviewing this paper, Locating and Editing Factual Associations in GPT. The thing I wanted to cover before we get started, just briefly, a couple blogs, I guess, is where it's going to be. But one of the models, one of the things they use, the kind of key visual that they use here, they've represented a GPT transformer model in this grid array. And I think a little insight, this is the part that kind of confused me a little. I'll go through what this is, but I'm going to roll back to a question from last week when we were doing a transformer review. If everybody remembers, this is from the original Attention is All You Need paper, I believe, and shows the encoder and decoder blocks, where each one of these, it's kind of over compressed because it's in these little gray rectangles, but this actually is represented as a stack of those. So you would have a multi-headed attention, a feed-forward network, and then the output of that would feed into another multi-headed attention, go into another feed-forward, and repeat multiple deep. And likewise, in this dimension, these transformers apply the same weights, the same model to every input token. So there would be many tokens, each of which would have this stack of attention, feed forward, attention, feed forward, attention, feed forward, with some other little layers that add the residual add as well as the normalization. And then on the other side in the original, so that this is what we call the encoder on the original. And then on the right-hand side, we had the decoder. Again, this gray block would represent multiple of these stacked on top of each other. So what would come in the bottom goes to the local attention, then to this cross attention, and then through the feed forward network. And then the output of that would come again into another one of these blocks, attention, cross attention, feed forward, et cetera, et cetera. And I kind of saw that, and the question I asked was about this attention, cross attention link between the encoder and the decoder. And I think, I don't know if Jayeth is on the line tonight or not, doesn't look like it. Oh, you're here, okay. I think you had done a quick search live that said, yeah, no, that's still the way it is. It's represented with just the top of the encoder that comes out and feeds into this decoder. So
yeah, so it's like, oh, you know, it looked like the whole, you know, if it's a sentence,
right,
like
right.
the whole sentence is then represented by this one vector that goes into the decoder.
Right. And so I was a little confused because this grid array wasn't matching up with that if it was only the top of the encoder being fed into the decoder.
Yeah, so Roger, the first thing you need to do is you need to rotate this 90 degrees to turn it into the paper we're reading.
Yeah, okay, fair enough. Yeah.
Okay. And then modern generative transformers like GPT-2, GPT-3, they're decoder only. So you don't need the second half. But when you don't have the encoder, there's no cross attention either. So the only difference between a decoder only model and an encoder only model is that in the encoder, you have this multi-headed attention where every token looks at every other token when they're figuring out how much they're going to weight their value output. Okay. In a decoder only model, every token looks at themselves and everything to their left, but they can't look into the future. So that's why you notice on the right-hand side, it says masked multi-head attention. So the second token will look at only the second and the first. The 20th will look at the 20th itself and the 19 to the left of it. And the 1000th will look at itself and the 1000 to the left of it. But nobody looks to their right. So, so the diagram actually gets quite a bit simpler when you're talking about GPT-3. It's just really one orange box and one blue box. And then there's a residual stream. Okay. So if you take the orange and the blue box, you turn it 90 degrees so that they're facing left to right. The little pink thing at the bottom that says input embedding, okay, that is the little trapezoid that you see on the far left of the paper we're reading. Okay, so you see one of those, one embedding. And then if you imagine there's 12 layers, then you're going to go orange, tan, whatever that color is, blue, orange, blue, orange, blue, orange, blue, orange, blue. And then what you see correctly in the paper, when you flip back to that, is that they're not connected in series because it's a residual network. They all are connected, so to speak, in parallel, where they're grabbing their input off of the straight line and then dumping their values back onto the straight line. I don't know, does that help?
Actually, that summarizes what I was going to go over in this, the overview. Yeah. I don't know how much of it, but if everybody got out of Ted's description, what we need, then that's fine. Otherwise, I'll go through these other slides.
If you can do it another time, I think doing it twice is for this type of fundamental building block is always helpful.
Okay. All right. Well, then, let's see. This part was the blog. I'll post that. Actually, I think I've already posted this in the Slack channel if anybody wants to read through. But it basically just states what Ted just stated, which is this is the original transformer with the encoder and decoder. Made sense back in the old days or when transformer was introduced because it was introduced for language translation. So you were feeding that into the encoder. And then I think a way to think of it is the decoder, in addition to this masked attention, which only allowed you to look at things beforehand, not look at the future, whereas the encoder can look on both sides, both tokens before and after. The decoder can only look at tokens prior to the next generated token. So anyhow, for translation, that kind of made sense. But as Ted said, these different models are using different parts of it, what you could think of as different parts of it. And the main difference being the masked attention that makes it causal. And one of the things that in this exploration that I ran across, Ted, I don't know if you'd seen this, but that I ran across is that the transformers can actually be run in a inference mode where they are causal, meaning that they essentially, if they know each time you're going to add another token, they don't recalculate the whole stack each time for all the tokens. Since the last token cannot affect the state of the prior tokens, they don't regenerate all the hidden states. They just allow the stack to attend to the previous hidden state. So it makes it more efficient. You don't have to compute the whole thing every time.
Question.
Yeah.
So is it that the encoder is never there, not in training, not ever?
Well, the first thing again is the difference between an encoder and decoder is that the decoder has masked attention, meaning that you can't, you only can look at prior tokens. You can't look at the future. Whereas the encoder can look at, they used it, if you remember, they were training it with, what was it, like masked words, where they cut a word out in the middle of a sentence, right? And it can look at both sides. Right, it can look at both sides and try to figure out what the token in the middle. It gives it a little bit more information. I read somewhere where they said that it might not learn as much structure because it tends to look, you can get more context just from the local tokens. You don't have to kind of pay attention as far out. But anyhow, that's one thing. Encoder can look at that the past and the future. The decoder can only look at the past.
Mhm.
And then the other thing is that both of them have a local attention, both of them have a feed forward, but the decoder, in the original document, the decoder had an ability to attend to the last token or the last hidden state, I guess, the output of the encoder for each of the tokens.
Right. So I was just wondering, you know, from a, like if I'm thinking about the training of GPT-3 or 2 or whatever, where is the input fed in? What is the task that it's trying to learn?
My understanding is, correct me if I'm wrong, if anybody has it, but my understanding is that those are basically trained on token prediction. So it's fed a sequence, and then its loss function is related to the probability of the next token in the sequence.
So is it like the traditional language model?
Yeah, yeah, yeah. That's
It's good old-fashioned cross entropy. So if you were building a classifier that was classifying between like 4 different breeds of dogs, you would use cross entropy loss, and you would, let's say, like one hot encode your outputs. You'd have 4 outputs, right? You one hot encode them. Okay, I mean, you don't have to do it that way, but that's a pretty typical way of setting it up, right? Okay.
Yeah.
The slight difference here is that if your vocabulary size is 50,000, then you're doing cross entropy across 50,000 classes, which you might reasonably think, well, that won't work. That's too many, but it does work. Okay. So it's pure cross entropy. So you say the first word is the, and then like, obviously there's no way it can possibly know for sure what the next word is. There's a gazillion words that could follow the, but basically if the next word is boy and it guessed boy, it's right. And anything else it guesses, it's wrong. And so in training, it gets a loss that gets, you know, backpropped through all the weights.
And is it fed, you know, like when you have the encoder, it is fed the embedding of that token, and then there is also like a positional something that is concatenated.
Yes.
And so is all of that not there if you do a decoder only network?
So if you do decoder only, nothing really changes. You embed you're not going to use the numbers 0 through 50,000, okay, or 49,999. You're going to embed them into a high dimensional space. So for GPT-2, maybe it was like a 500 dimensional vector. For GPT-3, it's probably more like 1,000 dimensional vector.
Okay.
And you're going to add positional information, and you're going to feed it in. And the way you're going to do it is you're going to feed in just the first word, you know, the, and it's going to predict the second word. Then you're going to feed in the boy, and it's going to predict the third word. And then you're going to feed in the boy said, and it's going to predict the fourth word. And if you're really clever and you dissect this and you look, you'll realize that you didn't actually need to wait until you fed in the boy to see what the loss will be when you do the boy said. None of those depend on each other. And so if you're clever, you can figure out a way to line up the calculations with the right mask so that you can actually figure out all the predictions simultaneously in parallel. You can figure out the prediction for the second word, the third, the fourth, the fifth, and none of them will cheat and look at the stuff to the right. And it just saves on compute. But if you don't understand it, it's fine. Just you don't need to know that they figured out how to cleverly parallelize it. You just need to know that it is doing each of those. And so if you had a 1,000-word sequence, like the first 1,000 words of a Wikipedia article, it's going to have 999 predictions. And it's going to get a loss on every single one of those predictions that gets backpropped through all the weights.
And during training only, right?
So yeah, Jayanth, I thought, was asking about how you do training.
Yeah, I was. And so You know, in the original transformer diagram, the decoder gets two inputs. You know, one is from the encoder, and that goes to every layer, right?
Right.
That thing that's coming from the encoder, and then there's this output embedding with positional encoding. So in the case of GPT-3 with only decoder, is it only that pink output embedding and positional encoding block that goes in, or how is it? I wonder.
That's correct. The second orange tan block doesn't even exist because there's no second input to do cross attention on. So this architecture in the original paper was for translation.
Right.
So if you put French in on the left in the encoder, then it's generating weights to represent the meaning of that French sentence. And then on the right, you input the English one word at a time. And then it's able to use both the English words it's seen so far, plus the meaning that the encoder created to represent all of the French.
Right.
It gets to see all of the French, not just the first however many words, it just gets to see all of it.
Including the future tokens.
Including the future, I believe. I'm not 100% sure how they implement that. But so the thing is, we're not doing translation in GPT-3 anymore. We're just saying, hey, GPT-3, I'll give you a prompt, just start spitting out words. So you just don't need that other part.
Yeah.
So it used to be like for the translation, you would feed the inputs on one side into the encoder, and then the generative side would generate the output.
One at a time, right?
One at a time.
Yes.
I don't know.
And so, you know, like if you're translating, the English goes into the input embedding and the French goes into the output embedding.
Yeah. You can do any two languages, whatever direction. And so I don't want to confuse anybody. I believe there's one exception that I think T5, the way they built it, it actually looks like this. And so basically what they're doing is this experiment on translating English to English. So when it generates stuff, it's actually doing like English to English translation.
I see.
But otherwise,
That's what that means.
every other language model that you've heard of, all the GPT clones, GPT-1, GPT-2, GPT-3, Chat-GPT, whatever, pretty much any other one that you've heard of is decoder only.
Cool. Thank you for that.
Yeah. So the two things, observations for me was, you know, in the original attention, all you need, you have kind of an input here and an output there. And so in my head, I was thinking kind of prompt in here and continuation out. But that's not the case. That the prompt is just the first part of the sequence, and then it just continues the sequence. So, and in a way, I don't know if this is the right way to think about it, but I almost can think of this in translation as being kind of a conditional generative model. The decoder's generating the English based on the condition of this, the output of the encoder.
I like that. That's cool, Roger. Yeah, so like if you're translating French to English, it's outputting one token at a time conditional on what it knows about the French input. Sorry, one last thing, which I don't know if you're going to get to it. I seem to be doing a bad job of jumping ahead. Jayanth asked about how these things are trained. Okay, when you're running them and you're doing inference, you're just generating, you do have to actually do it one token at a time, one word at a time. Okay, there's no magic trick for parallelizing it then. And so actually, can you go back to just the main diagram?
Yep.
Yeah. So on the right, where you see the output is at the tippy top and the input goes into like the pink, after you've said the first word, okay, as your prediction, that output then gets copied to the input on the pink side. And then when you say my prediction for the next word is boy, it takes the word boy and it sends that in. So Chat-GPT or whatever, as soon as it predicts one token, then that token is appended to the input sequence, and then they run it through again. So when Chat-GPT actually spits out, let's say, a 200-word paragraph, that means that they actually had to do inference 200 times. There's no getting around that. There's no parallelizing it.
Yeah, that's a good point, because I think, and that makes sense as well, because during training, you have the future tokens available to you.
That's right.
In inference, you don't. And so therefore you have to do it
Right.
one at a time. But that's a great point. Yeah.
Yeah.
Thank you.
Yeah, I didn't understand that, or wasn't aware of that difference, Ted, when you're training, that you can generate them in parallel. So that,
Yeah,
Yeah,
and that's a performance optimization. If you don't
Yeah, yeah.
understand it, it's fine. It's equivalent to if you did it one at a time.
Yeah.
Okay, mathematically.
and then the performance enhancement for the inference is once you've generated all these hidden states. So this is the grid that kind of represents this turned on its side. Once you've generated all these hidden states for the first token, when you append, this would have been space on the output. When you append the next token, you don't have to recompute all these hidden states. If you've cached them and they have transformer models that'll cache those, then you can just pay attention to the previously cached values. So you really only go up the stack for the most recent token during inference.
Mhm.
So anyhow, I think that's longer than I planned. The one other thing that in that illustrated GPT was just an awareness of where the parameter mass is. So this is the decoder has these guys are the ones that generate the query key values. This one essentially allows you, once you've got all these attentions and values, modulated values, you bring them together. There's a projection matrix that you use to kind of figure out how to add them together. Then you add in your residual, and then you go back up through these two transformers, which are the MLP layers that we'll be talking about in this paper. So looking at the masses here, you can see that there's a whole lot, there's a whole lot of parameters down here in this MLP. There's still quite a few in the attention, but there's, people sometimes they're claiming are kind of ignoring this MLP mass, which is these guys here. So, okay, with that, hopefully that gives the background. Again, the driving factor for me was understanding how this attention works at every single layer in the stack.
The MLP is the feed forward.
Yes,
That was
that's
shown
right.
earlier. Yeah. Okay.
Yeah, the feed forward part, right? Yeah, in this picture, it would have been this little blue box. The other ones were the ones down here.
Yeah. Thanks.
The key value, query key value, and the projection are all down in this one.
Hey, Roger.
Yeah.
One quick thing. So I think we used the word like projection matrix, and I feel like a couple of weeks ago we used it too. Is that the word that everybody uses? Is that?
I don't have insight. Does anybody else have insight why they call it projection? It basically is a transformation from one vector space to another vector space, which may or may not be the same size.
Okay.
Yeah, so if you have a fully connected feed forward neural network, also called the multi-layer perceptron, right? If it has only one hidden layer, then all you're doing is multiplying by one square matrix, essentially. Okay. And well, it can be rectangular if you want to change size, but if you're keeping the dimensionality the same, you're multiplying by square matrix. And for people who've done a lot of linear algebra, if you're multiplying by square matrix, then you're really just projecting from one d-dimensional vector space to a different d-dimensional vector space.
So, Ted, projection implies a linear transformation then?
It is, because a matrix multiplication is a very linear operation, right? You're just sort of like, whatever, if you left matrix on the left, vector, column vector on the right, then that means you're using one row at a time of each matrix to just convert that vector into components of your new vector, right? So element one of your new output is just going to be a linear combination of all the values of your original vector. And the various weighting of it is just based on row one of your matrix.
Okay.
Okay. So And you can have biases, and it doesn't really change anything because you can sort of include the bias term as like an extra dimension in your model, and you can
Right.
use ones, and then they just
Add it to
naturally
this.
fall into the matrix multiplication.
Yep.
So there's a lot of times where we multiply by a matrix, and you might hear people use the term projection. They may or may not use the word. They're not guaranteed to use it, but if you do, it's really just showing that you're going from one place to another. So the pink box at the bottom, the embeddings, that's just a matrix multiply. So that's a projection basically also. And so there's a gazillion places where we just do a simple matrix multiply. And so depending on who the author is, you just might see them use that word.
Yeah, I mean, and another way to think about it, you know, if you want to look at it a little bit mathematically, if you have, let's say, 3 dimensions, and if you multiply by a 3×2 vector, then you would end up in a 2D space. And so sort of a projection from one to the other. I don't know if that makes sense.
Yeah, or vice versa.
Yeah. Sorry, Roger, go ahead.
No, I was going to say, or vice versa.
Right, yeah.
Yeah. Why don't we open up any other questions before we start the video? Because the video, I think, is the next step. Okay. All right, then with that, I'll go ahead and get started. Let me just do a quick scroll back, and we'll just play through this. Again, I can't see anybody, so just speak up if.
So Roger,
Yeah.
if you want to see us simultaneously, which you don't have to, if you go and you hover over the little green box that says you're sharing, it will drop down a Zoom bar.
Okay.
And there should be 3 dots on the right side that say more, and you can do show video panel.
Okay, I got screen sharing. I'm not getting that. I get a little video, but move this window away from the shared application. Oh, okay.
It should be like a more menu. And you show video panel or hide video panel, and that will allow you to see us to the side.
Okay, I didn't get it, but that's okay. Just somebody just speak up if you want to stop, or if there's any chat. I'll try to monitor that. Here we go.
Hello, today we're talking about locating and editing factual associations in GPT.
Everybody getting the audio?
Yep.
It's a little quiet. We're getting it for sure. So I don't know if you need to turn your computer volume up a little, or yeah.
Bao Alexandonian and Jonathan Belenkov. In
Is
this
that better?
paper,
Yeah, that's good for me. I
Yeah,
don't know
that's
about
good.
anyone else.
Okay.
authors attempt to localize where in a forward pass through a language model an actual fact is located, or where it is realized. For example, something like the Space Needle is in downtown Seattle. It has a subject, a verb, and an object. And where exactly in a language model does the language model know, quote unquote, these things, and that the Space Needle is in downtown Seattle? That's a question of this paper, and they go beyond that. By figuring out where these facts are, they can also then edit those facts, meaning they can change the model such that it all of a sudden believes that the Space Needle is in Paris. And they test in various ways that this change is, first of all, robust, it generalizes, but it doesn't distort the rest of the model too much. Moreover, this change is like a rank 1 update that they can pre-compute. So all of this is very, very interesting, and we're going into it in detail. This video is a bit of a mix between me explaining the paper and the authors whom I interviewed, giving their inputs into various aspects of these questions. I hope this is of benefit to you. Let me know if you like it or not, and let's go into it. There's an entire subfield that just researches where are facts in language models. I didn't know about this subfield until I read your respective works. And what does it entail? Like, what are people wondering about?
So I guess there's a few questions. I think it's at the intersection of two main things. Like, one is a scientific investigation into where things are and what models are doing to achieve them. And then at the other end of the spectrum is like a practical question, that sometimes these models mess up, sometimes they have information that we want to change because it's now outdated. And how do we do this in a practical, in a very clean way? On both sides, there are, there are individual respective questions. On the interpretability side, I think David might be able to talk about it a bit, because he's worked with not only language but also vision models. But yeah.
Yeah. So I can talk about the interpretability side, and why don't you talk about the practical
sounds good.
side. So on the interpretability side, it's this really old question that's gone back to sort of the early days of neuroscience, which is, where do ideas and where does knowledge live in a big neural network? I mean, people thought about this in the biological neural networks of your brain. There's this old theory of the grandmother neuron that, maybe you could even have a single neuron that's responsible for what you think of your, for thinking about your grandmother. And maybe if you pluck that neuron out of your brain, you might forget that whole concept, which people think is sort of implausible. But what we're chasing here is sort of a weaker locality question. Like, if you have some knowledge in a big neural network, can it be localized to a small set of neurons or small set of layers? Can we find out where that knowledge is? And so there's been a bunch of people who's been looking at this. It's I guess maybe the overarching area is called like mechanistic interpretability research, where people are trying to understand the mechanisms that are emerging inside the learned computations. And so there was a really nice paper by El-Haji from Anthropic. There's been a series of papers from Jiva, from Israel, who have been looking at the structure of computations inside the network. And so our paper is another contribution in this direction. I think the thing that we're looking at a little differently is we're really focusing on using causal probes to ask that question, making changes in the network to see how the network responds when we make changes, and using that to map out things.
And what I love about your work is then you actually put it to the test, which means that if we understand where the knowledge is, we should be able to change it, right? And that gives, to me, the interpretability research is always a bit shrouded in mystery, because there are always, I feel, something like 10,000 different explanations that could explain a given fact. And usually the researchers frame it in a way that their hypothesis makes the most sense, but I'm always like, meh. But if you then actually put it to the test and you say, well, if we are correct, we should be able to edit the knowledge. We should be able to erase the fact or insert a new one using what we think happens. And that's also a thing that you do very well.
Yeah, so I think that's where the really interesting interplay between the interpretability and the practical side comes in. Because on the practical side, people have been chasing this question of real world usage. Like, these models are huge, they're really difficult to retrain. And then when we actually do fine tune them, for example, on a small data set with sort of a blind objective, it's kind of hard to tell sometimes what we're doing with it. And so in the past, we've seen some works, for example, from Mitchell and from DeCow. They spent a lot of time asking the question, like, can we achieve generalization when we do edits? When we change one thing, does something else change? Or is the edit specific? Like, if we change one thing, does an unrelated fact also change undesirably? So they've kind of set this area up because it's a very practical question. And I think the really cool thing about Rome is that, like you said, on one side is the scientific question, but on the other side, we show that the insights that we get can yield a pretty useful model editor that seems to achieve generalization, specificity, and fluency preservation all pretty well.
I was wondering, since the main foundation of neural networks is distributed representations, this is the big step, right? To go from GoFi systems, from symbolic systems, to distributed systems where we no longer have individual symbols representing individual things in the world, which we could build, very simple knowledge graphs. Now, a fact like the Space Needle is in downtown Seattle needs to be stored somewhere in a vector space, yet you managed to actually locate that fairly well to particular points in the network. How does that work? So here is how causal tracing works. This is one of the main methods the authors employ to figure out where in the model the facts are realized. We are talking here about the realization of facts, which is connected to the storing of facts, but we specifically care about the activation, so the hidden signals as they travel through the networks, and not necessarily localizing facts inside of the weights of the neural network. So
You're
Roger,
muted.
you're muted.
Oops. All right, I wanted to pause just quickly, just again, to go through this grid representation of the transformer, just so it makes sense for everybody. So as Ted said, this is kind of the model we saw before turned on its side. This is the first token on down. And then these are the multiple blocks of these decoder blocks. Within the blocks, this red is representing attention. So for instance, this first attention can get basically just itself. It doesn't have any prior tokens, whereas the second attention block, if you can see this, follow this little red line, can attend to the first two tokens. And then again, since it's a residual type of model where they swing the input around to the top of the attention block, it gets added back in here. And then the green represents the MLP, which two-layer MLP that we talked about, which again, it's a residual network, so it flows around. And then we go on to the next block. So each one of these represents a decoder block. Each one of these tokens has a stack of decoder blocks ahead of it. And the attention in the most recent token can attend to the same layer all the way back to the first token. Does that make sense?
So the straight line between, any of those two purple circles,
These, yeah.
I guess that would be the residual connection.
Yeah,
Right.
that would be, so there's this one, these are n stacked, n of them, so that you have the encoding, the word or the token encoding comes into the first one. The output of the first one then gets fed into the input of the next one. The output of it gets fed into the input of the next one until you have n of those, and then finally you come out through the linear layer and the softmax.
Yeah, so what I mean is that how the residual connection goes directly
yes.
right? And so I think the horizontal line, the straight line, it looks like it represents the residual.
Yes.
Yeah, if you look in the original transformer diagram, the little yellow boxes are the pluses, where we take the straight through data and we add the data coming out of the block, whether it be the attention block or the feed forward block. The way that's drawn, like my eye says, oh, the more important thing is the attention block and the feed forward block. But the reality is, mathematically, when you addition, no one of them is more important than the other. And I think what researchers are learning is that it's actually more important to think about the straight through data than it is to think about the modified data from the attention and the feed forward. So more modern diagrams, instead of the straight through path being this awful circuitous loopy thing that goes through the yellow boxes, they just draw it as a straight line. And then it's very clear that data could hypothetically, if you had all zeros in all your weights, the data is just going to go straight through unmodified. Okay. And maybe it just makes the diagram a little easier to draw too, but nevertheless, so that's why in this version, aside from being rotated 90 degrees, you see that as straight through. I've seen other diagrams where again, they try to emphasize the straight through instead of, it tends to get de-emphasized in other diagrams.
Yeah,
like there should be, at the output of this red and this green, there should be a plus operator.
Right.
As well as a normalization layer.
Yeah, I mean, usually the ResNet and everything, you have the straight thing going around, but here,
By the
Okay.
way, I think it was the same thing in computer vision with the original ResNet. The original ResNet drew the straight through connection as this awful curly
Correct.
thing going into the plus. And then
Correct.
later on, we realized, oh, let's emphasize that by drawing it straight and have the
Oh,
CNN
they
thing.
made it into the highway, right? Like that was the highway and you had stuff around it. It was exactly the other way around.
Yeah, so we had the exact same problem in computer vision where people didn't realize the importance of the straight through path.
Yeah.
Okay, any other questions? We'll keep going. All right, here we go.
In this case, you can see that here is a sentence that you input. The Space Needle is in downtown, and the model would output, well, in this case, it's an uncorrupted sentence. The model would get this correct. If it's a good language model, it would get this correct to say Seattle as the next token. This, as you can see, goes through a number of different stages. So due to how GPT works, how a autoregressive transformer works with causal masking, you will have the token for the being embedded, generating a hidden state here. Now that hidden state, first of all, it goes through essentially the layers of the transformers, and it accumulates two things. So it always accumulates an attention head, and it accumulates a multi-layer perceptron head, or actually I think two in succession, and then there's a residual connection around that. So that's what you see right here. But also the same hidden signal on each layer travels forward, essentially. Well, not exactly. It's more like when the second token or the third token, when they come in, so when space is now fed into the transformer, it now gets a signal from the past, because it does causal attention, it looks at the past. So it also will get kind of the hidden signals, the hidden states from the past. So essentially this would flow like so, but every time it would also get the hidden signal from there. And then need will get the hidden signal from both the and space. So we get both of them right here. But also it would travel up the layers and get both the hidden signals from here. So you can see there is various paths this information can take. And the idea here is to figure out where in these hidden states, so in these bubbles right here, or this bubble, where is the fact that Seattle should be the output of the sentence? Where is that kind of realized? Where is that localized? Now, you might have various opinions where that's localized. First of all, opinions here, like where in the sentence does the model kind of put a lot of weight on Seattle, and where in the network. So here in the depth of the network, where does that happen? And both of them, what turns out as evidence, both of these things are quite surprising. So here, what they do is this causal tracing. What they do is they run the model once with a clean input. They record all of these hidden activations. Then they run the model again, but this time with corrupted input. So here you can see these have little asterisks by them, which means that the input is now corrupted. It means you add some noise, or you just replace them by noise, or replace them by something else. It's just not the original signal anymore. And therefore, if you just let the model run, it will probably produce something else, because the subject, so this is the subject of the sentence, is completely corrupted. So this could be whatever is in downtown. And then Seattle is certainly not the first thing on the model's mind. It might be, but it's like very likely not. And then what they do is really interesting. They now take each one of these things here individually. They take a hidden state and they just copy it over. They just copy that over. So instead of at this particular hidden state, instead of what the model gets as an input, from this path and from this path and from this path here, instead of that, it just ignores that particular hidden state and replaces it with the one from the clean input. And now we observe, so here maybe it said like Paris before, because something is in downtown, the model just said Paris. And now we observe, if it kind of stays at a wrong answer, then that hidden state, that original hidden state, was probably not super well associated with either the input Space Needle or the output Seattle. However, if copying over that hidden state from the clean signal actually changes the output back from Paris to Seattle, well, that is a fat marker. Oh, sorry about that. Those are my notes. If that actually changes it back, then we know, aha, this hidden state must be quite important for sort of associating Space Needle to Seattle. And that's how we find out. And as you can see in the results, you get these two clusters. You get what they call an early site, which usually happens after the subject is done, and a late site, which usually happens right before you need to predict. So what's surprising, at least to me, is that these early sites here exist, which indicates that the model is aware of what it kind of could say with respect to the Space Needle much earlier than you would think, right? After just consuming the subject, it doesn't know yet that I'm looking for a location that, it is in downtown something, yet it already has a lot of information about the location of the Space Needle that is associated with the output of Seattle. So let's actually look at what the authors say about these things.
I think one component of it is that causal interventions have been shown to be pretty effective at kind of determining what happens in a model. And it seems intuitive because correlative studies are always there's always problems with confounding and all things like that. But when we go in and we make explicit changes to the computation of the model and we see what happens, we measure the effects, the things that we can read out are a little bit more clean. So the thing that we do in causal tracing is that the fundamental question is, we want to know which of these hidden states is carrying information that can help us convey the factual statement. And like you said, it's a big distributed network. So a priori, one of the things you might think is, well, everything is important and all the states have information that could recover the hidden state. So we wanted to test that. Let's see if this is actually true. So procedurally, what causal tracing does is it essentially first obfuscates the subject. It adds noise to the embeddings of the Space Needle, so now the network doesn't know what you're talking about, and it's got a whole set of corrupted activations. And then the question is, well, if you had clean states, if you could restore any clean state, could you pick one so that after you restored it, the network kind of recoups its computation and that state contains enough information for the rest of the network to determine that the correct answer is Seattle. And so the surprising result is shown in figure 1's E, F, and G, where we see this really, really sharp localization in this specific example. We see a patch that's early and a patch that's late that have really high causal effect. In essence, they have the information that's required to restore the factual statement, but all the other states don't. So a very sparse set of activations that can actually do this. And so we're curious, what does this actually correspond to? So we can actually do this activation copying for specifically the MLP and specifically the attention as well. And what we find is that the MLP corresponds to the early site and then the attention corresponds to the late site. And so the thing is, the late site is interesting because, well, it's not exactly too surprising because the model is going to recall the next fact by outputting the next token. So it's right next to the prediction and the causal impact there isn't too surprising. But what's really interesting is this weird early site that seems at first to be in the middle of nowhere. But actually, when we do this kind of experiment averaged over 1,000 facts, I think that might be figure 2 or figure.
Yeah, I think it might be on the next page.
Yeah. So in figure 2, when we do this averaging over 1,000 prompts, we find that it systematically lands at the last subject token, this patch of high causal effect in MLPs. And kind of inspired by a lot of the previous work in this area of interpreting where and what transformer components are doing, for example, from Geva, from Dai, and from Alhagi, we sort of formed the main hypothesis of the paper that these MLPs are actually what are recalling the factual knowledge. And this is sort of consistent with the transformer circuits idea that, in particular, Anthropic has been working on, which is that these MLPs might be outputting some kind of information that the attentions that are at the very last token that are actually responsible for the next token prediction are reading.
Mhm.
So,
So-
this was
so
can you pause?
this was a really stunning surprise to find this.
Did somebody request a pause?
Yeah, that was me.
Okay.
So there's two things that we've covered so far. So one is this causal tracing technique, and then the second is some very sharp results that they've gotten using the technique. Okay. So I think maybe we should just pause first to see if people understand the causal tracing, because if you go back a little bit to where they're showing figure 1, my understanding is that if, say, you have a 10-word sentence, so the height of the diagram is 10 rows, right? The way they're showing it on its side, it's 10 rows high, right? And if you have a 12-layer deep transformer model, the big ones are bigger, they're 24, 36, whatever, but just for simplicity, it's 12. Then at the point where you corrupt the Space Needle, you have 10 times 12. You have 120 hidden representations that you need to check to see if restoring them makes a big difference in recovering the original output Seattle. Maybe it's slightly less than that because you don't need to recover the ones that are later. I don't know, but like simplistically, if you're going to check all of them, it's like, length of your sequence times the number of layers of your transformer, right?
Right.
And if they're testing multiple corruption lengths, like what if I only corrupt the first 2 words? What if I corrupt the first 4 words? What if I corrupt 5, 6, 7? So then you do 120 times however many words they corrupt. That's like a whole lot of trials for just one freaking sentence. And in each one of these, they're storing off all 120 values for future use, right? And in addition, we see later on that they're not only storing the output value, they're actually secretly storing the part coming from the MLP and the part coming from the attention. So they're storing twice as many or 3 times as many things. So I just wanted to say that this is not something you would do by hand with pen and paper. This is a pretty large memory and compute thing, but just wanted to see if people got the technique, because I really love this causal tracing technique. It makes perfect sense when you hear them talk about it, but I don't know that I would have come up with this. There's a lot of things you could have done. There's way more numbers than just 10 times 12 that you could have decided you were going to store or look at. And so they figured out a way to kind of at least narrow it down a little bit, even though it's still quite a few numbers that they're tracking.
So, hey, Ted.
Yeah.
I have one sort of question. So you talked about, right, we have 120 embedding locations, right, 12 across 10. And so let's say that they're going sequentially, and they found out that, if you can change one particular embedding location, right, you'll get your Seattle as your answer, right?
Mm-hmm.
In this scenario, your input is still corrupted, right? And still you're getting Seattle as an output.
Mm-hmm.
To me, I know it's somehow finding the right embedding location, but seems like the whole architecture or whole network is kind of messed up, right? Because your input is corrupted and you change to one embedding location. And even though you're getting your right answer, but this whole system is no longer identical to your original clean network, right?
So yes and no. So if you look at the actual figure 1, the one that they're choosing to recover is the 3rd token, so needle, or the first part of needle, right? And it's in the 2nd layer, the 2nd transformer layer. It's not the first one on the left, but it's the 2nd one over, right? So hypothetically, when you copy over the value from the clean, you could be fixing anything that's in the upper left, the 2x3 rectangle. By copying this over, you're not guaranteed to, but you could be fixing any calculations that went wrong on the 2 squares above it, the one to the left, and the one that are 2 above the one to its left. Does that make sense?
Right, right, yeah.
So what they're saying is, gosh, if the information was really stored in exactly this second layer, third set of that unit,
Yeah.
right? And if that was the only place it was stored, then restoring it here would have this wonderful effect, and restoring it one above or one to the left would do nothing. It wouldn't help you at all.
Right.
Okay. Now they're going to keep doing all 120 no matter what. And what you'll see is in the sort of the lower diagram, like E, F, G, it's not really just one, right? They have multiple that kind of do respond. And so, you know, by my eye, I can sort of say it's there, but it isn't necessarily like just a single layer, a single unit. You know?
Yeah, that's one I struggle a little bit with is, what does that mean? The information is spread out, or at least our ability to detect it shows it as being spread out. And yet they're able to recover it with just by restoring one.
Yeah, I mean, I haven't read the paper like cover to cover, you know, but I suspect that one thing that could be happening is, let's say in these middle layers, in layers 4, 5, and 6, we are extracting facts about the Space Needle, and we're placing them onto the residual stream. Okay, it's possible that, say, the 4th layer is extracting what city it's in and what color it is, and the 5th layer is extracting how tall it is and what shape it is, and the 6th layer is, you know, so on and so forth, right? They're all storing different facts and shoving them on the residual stream. But if the 4th layer has extracted that it's in Seattle and placed it on the residual stream, if the 5th layer didn't modify that, it just added some other facts to other parts of the residual stream. Because remember, this is like GPT-2, it has like whatever, 768 floats. So you don't have to modify all 768 every time you pass through. You might just modify a few of them. The output of the 5th layer is still going to contain Seattle because the 4th one placed it on the residual stream. Does that make sense?
Yeah.
So as long as you don't overwrite it, any information that
okay.
was written by a previous layer. So in theory, 4, 5, and 6 are all going to, you know, have this information. That's kind of
It does.
my
That doesn't
intuition.
kind of explain kind of the soft roll in. The way you described it is like it shows up and then it lasts for a period of time. But I guess it could also be composited as the fact comes into it. It might be it's in Washington, it's in this county, it's in, okay, now it's in this city in there or something like that.
Yeah. I mean, you're right. Like, maybe it's not a perfect explanation. Maybe this isn't really like the grandma neuron. There isn't necessarily like, you know, but compared to how it could have been very diffuse.
Yeah.
Right.
Yeah.
It could have been that the Space Needle is just spread out over all, you know, hundreds, thousands of neurons. And then by the end, they all just add up and, you know, you get it, right?
Yeah.
So compared to that, this is very localized.
The other question I had here, and I don't know if there's maybe some sort of statistical or probability or graph theory answer to it or what, is why would you start by corrupting it and getting a false output, and then one at a time fixing each hidden layer to see that causes it to recover the output? Why is that better than just corrupting one node at a time?
So let me give you, I love analogies. Let me give you an analogy. I don't think this is one of my better ones, okay? But let's say you're building one of those things where you like knock over the domino and it just like, you know, I love videos of those where like, you know, just like 30 seconds of just like a bazillion dominoes all getting knocked down. Okay, right? Now, if I move a couple of the dominoes such that it interrupts it so that it doesn't cause the whole thing to fall down, right? If you say, well, if I can put one domino back and it causes the whole thing to work again, then that's the domino that mattered that I moved. All the other dominoes that I moved don't really matter.
But if I took one domino out and it didn't finished going all the way to the end, that also would said that was a critical domino.
Yes, but this is why this analogy is not perfect, because when you move certain dominoes, you're affecting multiple things. Okay, so right, they corrupted the space and needle, and they want to know kind of where in this whole thing is it most more. So this analogy is breaking down, but imagine that you did some changes to your domino thing, and are like, oh, darn, the whole thing doesn't work anymore. But just imagine that, like, somebody was able to come in, right? Grant comes in and he says, I'm going to put this one domino back where it used to be, and I think that will fix the whole thing. If he's right, then that means that all the other changes have been fixed by just having this one thing restored. That's what they're saying. And so the darkness of the color says how good a job did it do of restoring the whole shebang. You know, we weren't necessarily expecting 100%, but you know, in some cases, we're getting really strong localization.
So you know, my thought on that is, you know, so like if you just corrupted something in the middle, right, one at a time, I think that's what you're asking, right, Roger?
Yes, that is correct. Yep.
And so if you did that, first of all, given their result, I don't know if the model might still do okay with just one thing being corrupted. The second thought is that by doing what they did, they were able to demonstrate the sort of importance of a single, a single MLP or a single attention head, and that comes across as quite strong compared to knocking one out. So, but I don't know if that was their motivation. So that's sort of one thought on that.
What's even wilder is next week when we get to the second half of the paper, when we finish it, right? They're going to say, not only is restoring this domino able to restore, you know, the proper output, but now I've understood enough about the way dominoes work that I'm going to purposefully move this domino in this direction and predict that it's going to cause a completely different pattern of dominoes to fall, and your output's going to be Paris. And if I want, I can tweak the domino in this other direction and I can get it to output Boston. So that's then proving beyond any doubt that this is that you understand how this domino works, because you're just like, well, name a city. Oh, you want Miami? Okay, let me change the domino this way. And now the dominoes, when they fall, are going to spell out Miami, right? Like if you could do that, then like you really, really understand dominoes.
I have a separate question. So the point, you know, the scale, what does it actually say? Like the point to, you know, the intensity of the color.
They measure the change in the probability of the token, I think. So it's basically how well is it selecting the correct answer? I think that's what they
So do they run it like 10 times and then it appears, you know, Seattle appears twice?
No, I think what they do is they actually look at the output
probability.
Yeah, the output probability distribution.
Okay. Okay, cool. That helps. The other thing is that, you know, the way the coloring is done, and they may cover this in the later part of the paper, it kind of, I'm wondering if it tells you how the information moves in the, you know, in the network. So in the sense that the early sites are, you know, are not just what shall I say? They're in the middle, so they kind of have room to go on the right.
Yeah.
You know what I mean? And then the later one, it didn't occur on the leftmost side, it occurred later. And so that's where it is actually collecting all the information. This is what I'm imagining. And that's why it can affect what is going on. That's why it can affect the output.
It's a good observation. I don't know why he drew specifically here, but when you correct this node that he circled, He didn't correct any of the other ones. So certainly the ones behind, I think Ted was describing as kind of that block, 2x3 block ahead of it.
Right.
Those essentially are completely hidden. But
Right.
these ones over here are still present. So it's possible that an intention at this node, for instance, could be bringing in some information from one of these token paths, purple lines, that is still corrupted.
Yeah, I mean, so to me, it's like, you know, the information is kind of flowing from the top left to the bottom right, if
Yeah.
you can imagine.
Yeah, yeah.
And so if you plug this thing there, it kind of blocks out all the bad stuff.
Well,
And it's okay to
just
have
the top left bad stuff.
Yeah, whatever is behind it, and it be, you know, to the left and above it. And it's okay for some noise, because we know that these networks handle noise, you know, dropout, this, that, whatever. So it's okay with some of this thing creeping through, it still does okay.
Yeah, I don't love that dark blue purple arrow where on the legend it says example flow. Like, yeah, they just picked that out of a hat. It could have gone straight down from the beginning. It could have gone more to the right before going down. Like, all those are valid example flows. And somehow by showing that one, it's like they're implying that that one is more real than the other ones.
I agree, and unless they have some specific data that led them to draw it that way.
Yeah, the part that I've skimmed, I didn't see anything else. And so it really is, I feel like, an arrow for the people who just have trouble grasping the whole thing, to just like imagine a very simple straight circuit, you know, like this is the only thing that matters, but that's really not the only thing that matters. Yeah. So my intuition from this first part, as we now get to sort of like part EFG, you know, is like, I'm imagining now the first couple layers of the transformer are doing the language part, right? They're saying the Space Needle. What is that? Oh, Space Needle. Okay. That's a subject. And ultimately, they're going to need to combine the Space Needle into sort of one token in the third position, so that the rest of the model knows that this is a thing. Okay. And if you said White House, right, it needs to combine those two tokens into a single token for it to know. You know, you can't look up information on White House if you only have white and if you only have house. You have to combine them. So the early layers are doing some of that grammar and like figuring out, you know, like my noun, my verb, my whatever, you know. And then I see, okay, in these middle layers, they're just doing the dictionary lookup and throwing the kitchen sink onto the residual stream. I'm going to throw location, color, height, number of visitors per year, blah, 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 you know, as well as all the basic things. It's a building, you know, whatever. It's on planet Earth, you know. And then somewhere in the late, you're like, I have this residual stream full of facts about everything, you know, full of facts about the word is, full of facts about Space Needle, full of facts about whatever, you know. This is a very short sentence, but you can imagine you've got other nouns, you've got other things, right? And so somewhere at the very, very end, you have to decide, of all that stuff, where am I in my sentence? What do I need to do next? So in this case, it's like very clear, because they're saying like, what is in downtown, right? But then, like, let's say it emits the word Seattle. What's the word after that? You know, so it still needs to know like all this grammar to say, well, like, now what do I do? And then now what do I do? You know, so maybe it outputs a period and then it starts a new sentence.
The more I listen to you guys, the more I keep thinking about the residual stream as being something analogous to a long-term memory in an LSTM, like a multi-dimensional long-term memory, essentially. And your attention into that residual stream is almost like a lookup in long-term memory if we go back to LSTMs.
Yeah. So I can't remember if you were with us, or if it was this or a different meetup group where we did I think it was a different meetup group where we did the transformer circuit stuff, really gnarly stuff that Anthropic's done. But they found some really cool behaviors that they're able to identify in mini transformers, like only 2 layers or something like that, right? And so one thing is they found transformers that will copy values from one token position to another. Okay. And so the classic example for me is you have a pronoun and you see he or it later in the sentence. And if these things attend to the right word, they'll literally just copy the meaning of animal and place it in the position where the word it is. So that now it basically becomes animal instead of it for future layers, right? One of the coolest things that they wrote about is that they saw networks that would read part of the residual stream, multiply it by -1, and then add it back in, effectively clearing the register, turning it into zeros for future layers to use to have a nice empty register that they could write into.
So Sally, I kind of like that terminology. The residual stream is more of a register. The MLPs are more of the long-term memory. And it's a 40 or 128 step program, parallel program.
Yeah. And so you'll in your program, you'll say, hey, MLP, I want you to look up a certain something and stick it in the register. But you have lots of registers because remember, it's like 768 floats per token. So like, hey, you know, stick whatever values into portions, subspaces of this 768. And, you know, and so then some places they clear the register for other people to use, other places, you know, but it's pretty gnarly.
You know what you guys just did? You guys just built a CPU with registers and program counters.
That's right, a parallel processor.
But if in fact that is what transformers are doing, if you're saying that transformers have enough power in the attention mechanism to emulate a von Neumann CPU architecture, then it's not surprising that if you give them enough data and you train them long enough that they can actually do really amazing things, because basically you're saying it's a general purpose computer inside there with whatever 175 billion weights in GPT-3, right? So like, yeah, a general purpose computer with 175 billion memory could do an awful lot of cool stuff. The even cooler thing, oh, sorry. Then the final thought on that is the even cooler thing is, well, we already have computers, but we don't know what the right program is. This thing is learning its program through gradient descent.
Yeah.
So
yeah,
you give it.
If you think of it as a parallel processing computer, yeah, this is a differentiable programming.
Right, it's differentiable programming. You give it whatever 4, 10, whatever the number is, TPU years of compute.
Yeah.
And in a differentiable fashion, it coalesces on a program that can use these registers and store facts in its MLP.
I had read GPT, I think it was 3, was more like 300 years of GPU. So,
it's a lot of compute.
Yeah. Let's see, how should we proceed? So we're out of time basically here. I don't recall exactly where we could stop, but we could run until the end of this.
I think if we pick this up tomorrow, because this area is so dense, we're actually going to want to go back, not forward 30 seconds, you know, or a couple minutes in order to run through this, because this is pretty. I mean, you sent for folks that don't know, Roger sent me a couple of questions, and I'm just like, I don't know, like I'm struggling with this. So this is dense.
Yeah,
I agree with that. Yeah,
and good discussion. I've gotten a lot out of it.
I won't drink whiskey next time. Sorry.
No, it's drink a little more whiskey next time.
Leave the water out, Dave.
Or
Leave
maybe
the water
a different brand or something.
This is a pretty heavy duty one. I should lighten up a little bit, probably.
But very cool, very interesting.
Yeah. So we do tend to be informal, and maybe I tend to interrupt too many times. I don't know if we finish next week or if we really want to take 3 weeks total for this.
If we run, my humble opinion, if we run 3 weeks, we run 3 weeks, because it's better to have people understand than try to get through it and everybody going, well, I sort of understood that, but you know what I mean? So,
but I have to say, however, if we were to create a large language model that predicted how many weeks it takes us to get through a paper, I think it could just always predict 3, and it would be probably better than us.
Oh, that sounds like a statistical central tendency then. So
If we normalize around 3.
yeah, exactly.
And if you have the right whiskey, who's counting?
That's right.
It doesn't matter, right? Why not 4?
This is one of my favorites, so I'm very happy with it. So.
So it seems that, and I'm sorry, I just joined like 10 minutes ago. I was somewhere, but we did maybe around quarter of this video. Is that right?
And we decided the transformers aren't actually important, Div. Thanks a lot for introducing us to them.
Yeah,
so attention is not we need.
That's right.
I don't care. I don't have any attention. So
just so you don't get the wrong impression, we didn't stop this video that many times. Roger actually talked about some other blogs and stuff on introducing the architecture and the decoder architecture before we started the video, because otherwise I would have been pretty scared if we spent an hour and a half and only got whatever that is, 15 minutes into the video.
15 minutes into it. That's the
Hey Roger, do you mind putting that on Slack? Maybe I'll go through that.
Yeah, do.
And Ted, if it is okay with you, in the past we used to post the recording on Slack. Is it still possible to do that? So I would love to go through the recording sometimes when I miss the meetings.
That the intention is to post them. Right now we're recording locally. So
you're not recording in cloud?
No, I'm recording them and archiving them off.
Yeah.
Oh my goodness.
So we have talked about creating a YouTube channel for this meetup.
That would be great.
And then uploading them. We just haven't gotten around to doing it.
Sally,
no.
Sally, can you
We need
You
some
can
names.
stream. If you install the YouTube plugin, you can stream this straight to YouTube and it will store it for you.
Yeah, I think we need to do a little editing on ours sometimes.
good.
Can we answer Jan's question though? Because I think that's a good question. I didn't.
Oh, the needle thing. Yeah.
The what thing?
Why does it split needle?
Yeah, exactly.
Well, it's byte pair encoding, so it's purely just based on frequency, and so it must happen to be the case that needle's not that common a word, and so it just happened to get split.
Oh, interesting.
Did
So
it have
in the
some
actual encoding,
French
it's
in it?
probably need star. Is that is that what we're seeing here?
Yeah, but every
which is why there's a star there. Okay.
No, the star is for corruption.
Yeah.
Star is for corruption.
Yeah.
Okay, no.
Yeah. So every token is effectively a star in byte pair encoding. So if you decided that you're going to make up a new word, which is just like THEZ, it's probably going to get split into THE because that's so common, and then the letter
star.
Z in order to finish it. So it would be 2 tokens, THE and Z.
But the Z token will be the generic unknown token, right?
Right. The whole point of byte pair encoding is you never need unknown tokens. You always have something because all the individual you start with all the individual letters of the alphabet.
Oh, okay.
So,
all right.
So there's always, worst case, you can just spell it out 1 letter at a time. If it's just a complete gibberish looking word, it could do 1 letter at a time.
So the le is from like it has some French in it or something too.
It's somehow chosen that's a token.
Yes. Or it also could just be in the middle or the beginning of other words, but whatever. If it didn't have le, then it would be 3 tokens. It'd be need, L, and E as separate tokens.
I see.
Okay.
And so then the combination of need 1 token LE would then be somehow known in the inside of the model then. So it's no longer being able to be captured in the encoding. It has to be now it has to be captured in the model.
Yeah. And so if you're wondering how byte pair encodings are I'm sorry, go ahead, Roger. What?
No, I was just going to say this might be an interesting topic for a future one. There's some of the other language models that they looked at it that the attention is order of sequence length n squared, whereas vocabulary is just linear n. And so they experimented with larger vocabularies, some of which were multi-word tokens, and found, I know there was like a 25% improvement in performance or something like that. So
yeah, because then you could do fewer tokens because each token has more packed into it. Yeah.
Right.
So if you're wondering how they build a byte pair encoding, we start with every letter of the alphabet, okay? And then you say, what is the most common 2-letter sequence? It's not going to be a full word, but just any 2 letters that ever appear in that particular order, this one first, that one second. And let's just say it's TH. I don't know what the heck it's going to be, okay? Then you now expand your vocabulary so that it's 27 tokens. It's A through Z and TH. And now you say, what's the most common 2-thing pattern where you treat TH now just as a single letter? And so the next pattern might be ES, or it might be THE, or it might be whatever. And you just build these up one at a time. What's the most frequent? What's the most frequent? And so apparently needle just was never common enough that even though it had need, it never added, you know, and formed needle or whatever. Okay. If you hear about language models using word piece or whatever, byte pair encoding, that's where they do this. If you hear about sentence piece, which actually a fair number of models use, they allow space in the original vocabulary. Okay. And so therefore, not only can you get needle, but you can actually get space, no, that was a bad choice. White space house as a single token. Okay. So word piece, you cannot have multi-word tokens. Sentence piece, you can have multi-word tokens. So new space, York space, city is probably common enough that it's a single token in sentence piece. Okay. United States of America might be a single token, even though it's 4 words. And what Roger was saying, so if you allow a large enough vocabulary size, you can actually get quite a few multi-word tokens and shorten the length of your various sentences once you tokenize them.
And as you can imagine, it depends on your data set. If your data set has less of White House, but more of, let's say, Kremlin, just making it up, right? So then White House may never make it in the vocabulary.
Yeah, like if you just have all biology papers is what you trained your model on, then you probably don't need White House at all, right? But you might have other, whatever, anatomy terms that somehow make it into your vocabulary.
So I read some news says that GPT chat can kind of like produce knowledge, like they're kind of like they can give you answers to a single field just based on kind of like the article. So is that because that they just link relative words together, like you start with the word and you just try to find logically the next word, so that's how they can answer questions in all the different fields by just read through the text, that's by just training on the existing articles?
Yeah, I think there's some controversy. There's some people who think that this is awesome, and there's some people who think that it's statistical guessing that that can produce complete garbage, you know? So
once
I don't know.
It's trying to sound right, not necessarily to be right.
Yeah. So I'm
once
kind of
we
on the fence.
Once we stop recording, I can share more.
Is that my cue to stop the recording then, I guess? So.
Yeah, and then you'll know once I start speaking up and stop recording.
I'll go ahead and, well, once you finish, Ted, you were on
yeah, but so it's a very good question, and I think there are people who are still debating it. Okay, right? Some people who say that they think these models are pretty darn smart, and other people who would say they're good at imitating smart, but imitating smart is not the same thing as smart, right? So like if you have somebody who just hung out around a lot of physicists and learned a lot of the vocabulary and learned to make grammatical sentences with a lot of things like, oh, Higgs boson, blah, 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 blah. To you, they may sound smart, but they may actually not know anything. And so that's, I think, what some people are arguing, is that this thing really doesn't know anything. It's just smart enough to fool a layperson. All right, we can end the recording, and then Dave can say something apparently completely